So in the take it to the bank problem, let's look at 6-54. That's the next exercise. In A, you're told that Ricky decided he wants to alter Montana's shot so that it hits the right rail exactly at its midpoint. So you're asked to replicate the shot and give Ricky suggestions as to where to place the ball to start the shot so that it hits the right rail exactly at its midpoint. Well, the table is still 50 by 100, so you know you're going to have two 25-inch pieces. Now we don't know exactly where to put the ball along this top rail, but there's a pocket here. Maybe it'll be on this side, maybe it'll be on this side, we just don't know yet. So we're going to consider this distance some unknown distance. Now we've established that a bounce is a reflection. So we've got a pair of congruent triangles here, and I really like this problem because it illustrates how the dilation factor from triangle to triangle isn't the same from the first triangle to the third triangle as it is from the first triangle to the second triangle. So our scale factor from the triangle created here to the triangle created here is 1 to 1. The scale factor, though, for the third triangle created is not scaled at 1 to 1. That's going to be larger. What we do know is that the ratio from long leg to short leg will be the same from triangle to triangle, even from first to third, because they were all dilated at the same rate. So just like the example we looked at in class, where the 3, 4, 5 doubles to the 6, 8, 10, triples to the 9, 12, 15. 9 is to 12 in exactly the same way that 6 is to 8, in exactly the same way that 3 is to 4. So when you've got more than one triangle to compare, but you know they're all similar because of angle similarity, or because of side angle side similarity, or in this case we have side similarity, then you know that the comparison of any of the two parts will be the same from one to the next, regardless of the rate of dilation from one to the next. That's what all of trigonometry is based on. So what else do we know in this problem? So you're reading 6-54 to yourself. Take a minute, hit stop on this video while you take a look and see if you can decode what you're given in 6-54A. So the one reliable measurement we have is this 25 to 25. And this hasn't stopped being a pool table, so it's still a rectangle that's 50 by 100. So all we can really say is that this missing piece right here is 50 minus 100. Don't know the measure of this angle, but I do know that it's going to be the same as its bounce because of reflection. And that makes an angle-angle similarity situation in this triangle and in this triangle. So if I represent the three triangles next to each other, oriented the same way, I have a short leg of 50 and a long leg of 100 minus x. 50 is across from this angle, 100 minus x, and I should place that right in the middle of the side that it represents. 100 minus x is across from this angle. And in my second triangle here, this guy, I have across from this angle and remember we're trying to draw these so they're oriented the same way. I have 25. Across from this angle, we've marked X. And across from this angle in the original triangle, everything's the same because these two have a 1-to-1 scale factor, and they're congruent. So long leg is to short leg as long leg is to short leg. I'm comparing the legs. I could also say long leg is to long leg as short leg is to short leg, because I've only got one dilation in this case. Multiply by 50, that'll take care of both denominators. (100 minus x equals 2x, right? 50 divided by 25 is 2. 50 divided by 50 is 1. 100 minus x equals 2x. Add x to both sides. 100 equals 3x. So the algebra becomes pretty simple once we do the analysis. X equals 33 and 1/3. That's this value here or this value here. So Ricky's going to place his ball 33 and 1/3 inches from the top right pocket along the top rail. And then an inverse trig ratio will get us the angle. At an angle of ... Well, we're looking for this angle right here. So if I know this is 33 and 1/3, I can use a trig ratio. Inverse tangent of 25 over 33 and 1/3. And this is how I'm going to enter this in my calculator. Although I suppose I could also enter it as inverse tangent of 25 over 33 and just put a bunch of 3's after the decimal point. Either one of those will work, so go ahead and push those buttons. And what do we get for the angle that Ricky's going to try to approximate? And I've pressed the button both ways, so I'm convinced that either one works. I get approximately 36.87 degrees for theta. So Ricky will place the ball 33 1/3 inches from the right rail at an angle of 36.87 degrees. Try B.